So Sir Isaac Newton was one of the greatest physicists of all time. Really interesting guy, did a lot of his work in his early 20s and then headed off into very strange realms. Now, he was doing a lot of alchemy, a lot of theology, a lot of really interesting and weird stuff. And we don't actually know, I don't know anyway, whether he actually went, not crazy, but off into some very strange and esoteric and not very productive things, or whether he just got beyond us, whether he got to the point where he was doing stuff that nobody else could follow and understand. So Newton, fascinating guy, had a number of laws. So I tend not to try not to just talk about Newton's laws, because Newton has a law of heating and cooling as well, about if you have a hot object and a cold object, how quickly the hot one will cool. So there are a number of Newton's laws, not just these. So I talk about these as Newton's laws of motion, but people often just say Newton's laws. So they basically relate these three things: force, mass, and acceleration. And they're very powerful. They're relatively simple, but not always intuitive. And if you understand them, you will actually perceive and experience the world in a slightly different way. The particular statements of the laws that I've chosen are ones that I've developed in my teaching over the years. There'll be slightly different wording to some of the ones in textbooks or online that you'll find, because I've emphasized certain things, de-emphasized certain things, used words that I think make the concept more accessible to students. But the wording's not so crucial, it's about the concept. So, an object remains at rest or in a state of constant velocity motion in a straight line unless it's acted on by an unbalanced external force. Remember when we were talking about momentum, we said that it requires a force to change the motion of something. Now, we don't need to say in a straight line, because remember when we were talking about velocity, we said either changing the speed or the direction is a change of velocity. So if we say in a state of constant velocity motion, we've already implicitly said in a straight line, because constant velocity motion by definition is in a straight line. So that's why I put that bit in brackets, so you can ignore that if you want. An object remains at rest or in a state of constant velocity motion in a straight line unless it is acted on by an unbalanced external force. If it's acted upon by a balanced external force, I've got 10 newtons this way, 10 newtons that way, it's still not going to accelerate because it's balanced and the forces cancel out. So there's no net unbalanced force. If there are forces, if there's an unbalanced force, something will accelerate. Motion's relative, we've already talked about that. So we get to choose our frame of reference. Given that, we can't decide whether any particular motion is, or whether an object is at rest or in a state of uniform constant velocity motion in a straight line, because we don't have a reference frame. So it might be stationary relative to the Earth's surface, but remember the Earth is rotating once every 24 hours. The Earth is orbiting the Sun once every 365 days. The Earth is, and the Sun and our whole solar system is orbiting the galactic center over the course of some millions of years. Our galactic center is traveling through space away from most of the rest of the galaxies, but towards the Andromeda galaxy, which will collide with in about 2 billion years. So what do you say is the stationary still point? There is no stationary point of motion, no absolute frame of reference that we can say this is stationary. It's all relative. So that's why this says remains at rest or in a state of constant velocity motion in a straight line. And those two things are the same thing as each other, depending on the frame of reference you choose. It's like the illustration of being on the train and starting to run. Are you at rest relative to the train? Yes, but you're not at rest relative to the ground because the train's moving along. So it depends on the frame of reference whether you are at rest or in constant velocity straight line motion. Right? Make sense? So there's a lot packed into that one little sentence. The first law actually is a special case of the second law. He doesn't really need three laws. It's really helpful because it just makes things very explicit and clear rather than implicit. But when we talk about the second law, it actually explains the first law as well. So the second law, well, actually, let's talk a little bit before we get to it. Things have inertia. If something has more mass, it's harder to get it moving. The force, when the mass is greater, it requires more force. A colleague and I helped a guy whose car had broken down in the middle of the road and who was in danger of getting skittled. And his car was quite heavy. It took us a lot of force to push it. If it had been one of those little tiny smart cars, it would have been a lot easier. Right? This is just intuitive. This is stuff from the world that we live in. And it's true even in the space station. So on the International Space Station, if you're moving something large and heavy, it doesn't have weight. It's weightless, or we talk about microgravity these days, because there's not actually no gravity. It's the fact that it's in orbit. That's a whole other conversation for later. It doesn't have its weight, force, but it has all of its momentum. So if you're moving a 200 kilogram object and it slides over and crushes your hand against the wall, it still has all of that force and it will still do all of that damage. So this is true even out in space. And out in space actually is really good to think about, because that's where there's no other frictional forces, right? Our experience is that if I throw a ball, it will stop quite soon, but that's because there's friction. If I go out in space and throw a ball where there's no friction, no air resistance, no drag, it will do exactly what the first law says. It will continue in straight line motion at constant velocity forever and ever until it hits something or another force acts on it. So it's a nice environment in which to imagine these laws behaving. Our normal everyday world doesn't quite fit this because there is friction and a whole variety of other forces acting. So thinking about that, the first law, an object will remain in constant straight line motion until another force acts on it, right? And the bigger the force, the bigger the mass, the bigger the force. We talk about different kinds of mass. So when I was talking about the 200 kilogram object moving in the space station, it still has all of its inertial mass. It doesn't have its gravitational mass, or its gravitational mass isn't acting because it's in orbit, it's free falling. It's like when you're on a parachute jump. Your gravitation is acting, but you don't feel it because you're in free fall. So mass is not only related to gravity, it is related to gravity. It is related to the way different objects with mass attract each other, but it's also about this inertia thing, and that applies even out in deep space where there's very little gravity about. So the second law that we've been kind of inching up on, you can say it in words. The acceleration of an object is equal to the total force acting on it divided by its mass. So that's the first equation there. A, acceleration, equals the sum of all the forces. That's sigma, the Greek letter sigma, means the sum of all the forces. So remember I said earlier that if you've got equally balanced forces and the sum of all the forces is 0, you won't get an acceleration. If you've got unbalanced forces, you will get an acceleration. So sum of all the forces divided by the mass. So think about what happens with equations. If you make the bottom of a fraction bigger, it makes the fraction overall smaller. So we increase the mass, we decrease the acceleration if we keep the force the same. This is something I really want you to get, and something I really want you to tell your students. Understand what the formula is. Remember, maths is only a tool of physics. We are using it because it's useful, but we're not doing maths, we're doing physics. So you need to understand the concept and understand what the equation means in physical terms. So if we make the denominator, the bottom line of the fraction, bigger, we make the overall thing smaller. That kind of proportional reasoning, that thinking about what it means, is really important in physics. And I want you to be getting that and developing that intuition, that comfort with the numbers and what they mean. Or to put it another way, the net force acting on an object is equal to the product of its mass and its acceleration. So F equals ma might be the way you've already heard it. F equals ma, fairly easy. I've put a sigma in front of it. The sum of all the forces equals the mass times the acceleration. And you can see, if your algebra is up to scratch, that those two are exactly the same equation, just expressed in different ways. If you just rearrange, if you multiply both sides by the mass, you get one from the other. So again, be comfortable with your algebra. Be comfortable working around equations and moving them because you understand what's going on. If we used A equals sigma F over m, and I've already said this, if the sum of forces is 0, if all the forces are balanced, then the acceleration is 0. If that top line of that fraction is 0, then the A is 0, the acceleration is 0. And that's what it means when I say the first law is a special case of the second law. What did the first law say? An object that's not acted on by any external force will not accelerate, right? It won't change its velocity. It won't accelerate. So the fact that we've got this law that says if the acting forces are 0, the acceleration is 0, is the exact same thing. It's saying if the forces acting are 0, then no acceleration will take place, the velocity will remain constant. The direction won't change, the speed won't change. Does that make sense? But as you can see, it's a little bit of a reach, and you don't want to, I don't think, throw away the first law and just rely on the second law for your students. You want to be able to use both, but understand what's going on between those. We know the units. The SI unit for mass is the kilogram. The SI unit for acceleration, which we haven't talked about yet, but you're probably pretty familiar with, the meter per second squared. So meter per second is velocity or speed. It's how many meters you cover per second. And then meters per second squared is meters per second per second. How much does your velocity change, your velocity in meters per second, change every second? That's the unit of acceleration, right? That makes sense. So using F equals ma, we get the force, the unit for force is going to have to be something of mass, so kilograms, times meters per second squared. But we call that the Newton. That's a unit of force called the Newton, named after Sir Isaac. Notice that when you're naming the unit with a full word, it's lowercase, because Sir Isaac is Newton with a capital N. So you're not using any Newtons to do things in your laboratory because he's in the grave or in heaven, depending on your beliefs, right? You're not using capital N Newtons, you're using lowercase n Newtons, but the unit is a capital N, the abbreviation, right? So this stuff's important. And again, I apologize if I'm belaboring the point for people who are already comfortable with this stuff, but being careful to use the units clearly, consistently, encourage the students to do so, and to understand why the units are what the units are. It makes a lot of sense. Force is a vector quantity, and again, I have said this before, if the forces add up to something other than zero, if the force vectors, when you combine them, add up to, don't all cancel out, that there is some net resultant force, then the acceleration will occur, and the acceleration will be in the direction of the resultant force. Right, so if I've got my two force vectors coming in like this, they don't cancel out. If they were coming in straight and they were the same magnitude, they would cancel, but they're coming in at an angle. So there'll be some resultant force which will actually be straight up if those two are the same magnitude and the angle's like that. So if you added up those vectors, you would get an upward force vector, and that force vector would cause an upward acceleration. So we'll do some equations, examples, practice with those as well, because the vectors are a tool for understanding the forces that are acting in a situation, whether the situation is simple or complex. And finally, the third law, I've put action force and reaction force in brackets because I don't like it. It just sounded like Pauline Hanson then. I don't like it. Apologies if that offends anyone. What's an action force? What's a reaction force? Is this one the action force? Is this one the action force? It doesn't matter. We get to choose. So using the term action and reaction force, I think, confuses students. So just say for every force, there's another force, same magnitude in the opposite direction, and these forces act on different objects. So I weigh around about 90 kilos. I'm trying to lose some of that. Have weighed more in the past. So the force downward on me, if we let G equal roughly 10 meters per second squared, the downward force of gravity on me is 900 newtons. The Earth is pulling me downward with a force of 900 newtons, but I'm also pulling the Earth upward with a force of 900 newtons. Now, given that the Earth is 10 to the 30 kilograms and I'm 90 kilograms, I'm going to move a lot more than the Earth. If I jump off a high building, I will move very fast and accelerate very fast. The Earth will not even notice, right? But still, there is this force pair, and I was almost tempted then to say an action-reaction force pair, but again, which is which doesn't matter. Action and reaction is an unhelpful concept. There's a force pair. There's David v Earth and Earth v David. Two forces acting on different objects. One force acts on me, one force acts on the Earth. They're in opposite directions and they're the same magnitude. Similarly, I'm exerting a force downward on the floor in this room of 900 newtons, and it's exerting a force upward on me of 900 newtons. If it wasn't, I'd be falling because those forces wouldn't be balanced. But they're balanced. So every force has an equal force of equal magnitude in the opposite direction acting on a different object. If I've got a magnet pushing another magnet, repelling, then the other magnet is repelling back with just as much force. So every force has an opposite force in the opposite direction, same magnitude. So that's the third law of motion. And we use illustrations like if someone dives forward off a boat, they will push the boat backward. If someone uses a rocket, they need fuel because they're pushing fuel out the back fast, and that's pushing the rocket forward. So this is all Newton's third law. So the three laws together, they are very powerful, deceptively simple, but they explain a whole lot about our lives and our work around us. But remember, there is kind of physics world, which is the out in space world, where there's no friction and none of this stuff. And then there's the real world. And we have to kind of make it clear to the students why, when I am riding my bike and I stop pedaling, I will eventually stop. That doesn't break Newton's first law. That just means that there's another force acting, the friction in the bearings, the air resistance and so on, that I'm not maybe taking care of or taking it into account. So that deceleration is caused by that force or those forces that are acting. Does that make sense? So being fairly explicit about physics world versus real world and being able to talk about that is a helpful part of teaching senior physics.